Let us look at a programming implementation of the distinct powers problem which we saw in the previous videos. So we just have a distinct powers class, and let's look at the basic data types. So basically I'm having a hash map which is going to have the minimum powers, right? So why is this needed? So I'm just going to keep this statically populated. So what is the minimum value of a number raised to a power, right, which is less than 100? Because we know the problem's range is between 2 to 100. So I don't want to waste if the base like 2 power, like what you saw in the example, right, like 8 to the power 4 or something is greater than 100. If that base is greater than 100, there's no point even evaluating it and then saying that it is greater than 100. And it's just going to be for a handful. So so for 2, the minimum value of power that is less than 100 is 6, because 2 to the power 7 is 128, right? So 2 to the power 6 is the last power. So 6 is the last minimum power, where the 2 to the power x will be less than 100. So for 2 it is 6, for 3 it is 4, right? So it's 81. So 3 power 5 is greater than 100. So like that. So the minimum value of the minimum value to which that base can be raised, whose value will be less than 100, is what this map is going to contain. And all that you need to do is do till 10 only, because 10 to the power 2 is 100. Then after that everything is 1, right? So we will use that in a helper method. We will see during the implementation, but all that you need to code is only till 10, right? Because after that everything is 1. So 11 power 1 is 11, which is less than 100, but 11 power 2 itself goes beyond the range of 100. So that's why I have not put anything beyond 10. So that we will keep it here, right? You will see that. So if you look at how I'm using that down in the line, so we'll have a minimum power threshold. So let's say for 2, what is the minimum power threshold which yields the value less than 100? So we will get it, and if 2 is present in that map, we will get the value of 2, which will return it as 6, else we will return it as 1. So we have the values only from 2 to 10. So anything above 10, when it comes, the constant value 1 is being returned. That's how this data type or data structure will be used. We will see that, right? So that is the first data structure, minimum powers. And second, this is one of the key data structures that we will need for this problem. So factor pairs, right? So if you see, the way of systematically enumerating the power map is obtained by the factor pairs. And I mean, I just want to keep a very simple notational representation for this data structure. So all that I'm having is a hash map where the key is the number for which the factor pairs are to be. So for example, if 18 is the number, then the value will be a string concatenation of all the factor pairs, right? So 1 comma 18, 2 comma 9, and 3 comma 6 are the factor pairs. That's what we saw in this slide also, right? So when we list it out, right? So for 18 is 1, 18, 2, 9, 3, 6. So if it is you could use tuples or anything in Python, but in Java I don't want to complicate it too much by introducing a separate class for holding the factors and holding them as a list, etc. I'm just using a string concatenation. The only thing is, like, I know the convention, right? So this is, so every number will be the key between 2 to 100 will be the key, and the factor pairs will be a string representation of, so 1 comma 18, if it is a factor pair, 1 underscore 18, this is a convention I'm using, and add it with the next factor pair, so that because this is the convention we are using to form this hash map, I know how to split it and get the factor pairs later to use it in the power notation. So this is the second data structure, and this is our this data structure, whatever we saw here, right? So this grid, 2 to the 100. So this is the grid that is encoded by this data structure. And if you see, I have created it with 101, right? So so you know, like in most of the programming languages, the indexing starts from 0, and I could keep it at 100, but then we'll have to do like 1 minus etc while doing the index notation, because our range is between 2 to 100. So there is nothing wrong in having additional one more slice of memory. So just keep it till 101, then you will have 100. You don't have to manipulate the it's a regular programming technique. You will just get it once you start that, right? So that's the reason I have it till 101, so that I can touch the 100th guy, right? And so these are all some other data structures not directly needed. So while building this program, I was facing a lot of bugs. So I had to directly compute the I have to use the direct approach and find the powers to find the corner cases, etc. So that's why I have this, but these are not directly needed for this problem, right? So once we have ironed this out, so all the three data structures that you need is only these three, right? So keep a handy data structure to avoid base expansions. Keep a data structure to have the factor pass, and encode the power map, right, which is nothing but this grid. So now let's get into the actual implementation. First, we need to compute the factors, right? So we'll call the first method, which is computing the factor. For every number starting from 2 to 100, right? Because the ask of the problem is between 2 to 100. So for every number between 2 to 100, so let us find the factor pairs. So that's why once we get into the inner loop, we keep the target as I, and then we go from 1 to the square root, right? So like I said in the previous videos, all the, so if j star j, so if j equal to 1, and you just have to go till the target. So if j star j is greater than or equal to the target, then after that you don't have to go, right? So that is this notation. This is a common factor finding implementation. All the order of complexity is until the root of the target, right? So beyond the square root you will not have the factor pass, because if there is a bigger number you would have found it while finding the smaller factor pair. So that's what this inner loop will do. And as long as if the target is divisible by the j, which is less than the square root of the target, then you find and concatenate in this form that we want, right? So this is an empty string concatenated with j, right? So if for any number 1 is a factor, so 18, so this will be 1 plus divided by, so 18 right, by 1 is 18. So and then just put this thing, so because this is the convention we are forming, and finally there will be a plus, that's why we are substringing it, so that that comes in this notation, and put it in the map. So in the factor pairs map, put that number and then put that string. So what are the factors pairs of 18 is put in the string. So the factor pairs of 2 in this map will be 2 will be the key, and 1 underscore 2 will be that, right? Because 2 is a prime, and like only 1 and 2 are the factors of 2, right? So that is this method. So first method, we compute the factor pairs of 2 to 18. So second is populating the power map. So this is exactly the core logic where we go through this slide number 6 and 7. So it's very simple once you start looking at this. So we start from the base 2, right? So we have to cover this thing, right? So for every row, base 2, 200, right? So that's what we do. So start from the base equal to 2 and go till the power map's length, right? So the length of the power map is 101. So go till the 100, right? That's now you see the easiness, right? I don't have to manipulate base, just that termination condition will be sufficient. So base from 2 to 100 and power from 2 to 100. Now check if the cell value is not equal to -1. So because it's an integer array, everything will be 0. So either it should be 1 or -1 depending upon our computation, right? So that's why we are saying, like, if it is previously, so it will never be 1, right? Because you will make a cell as 1 only when you visit that cell. So but the default value of that cell will be 0, because in Java an integer array is initialized with all cells as 0. So that's why I'm just checking only for -1, right? I don't have to check for if it is not -1 or if it is not equal to 1, right? So all that I have to check for is -1, because I will make a cell as 1 only after visiting that cell. So only thing possible is either that cell is previously made -1 while doing the operation of some smaller cell. So that is the logic we are checking it for if it is not equal to -1. So as long as, let's say, like this 2 power 2 is the first cell we are visiting, if it is not equal to -1, which will be in that case because it will be 0, so you find the factor pairs, right? So you just get the factor pairs of the power. So let's keep this example handy, right? So 2 power 18. So base will be 2, power will be 18, and 2 to the power 18 will not be equal to -1. So this line, factor pairs or get the power get of 18, will get you this string. So 1 and 18, 2 and 9 and 3 and 6. So that will be the string you will get it. Now once you get it, you know, because you formed the string, just do a split and get the factor array, right? So 1 underscore 18 will be in the cell 0 in factor A, 2 underscore 9 will be in cell 1, 3 underscore 6 will be there. Now we are going to do this factor swapping game, right? So for every factor pair 1 comma 18, we just need to represent this like this and then do that. So that's what we are doing. Once you get the factor pair array, then iterate it till the factor pair array's length, right? So get the factor pairs, split it by underscore. Now 1 and 18 is going to be split by 1 in cell 0 and 18 in cell 1. That's what we are getting. So factor 1 is 1 and factor 2 is 18. So now we call a helper method, which is swap factors of base and factor 1 and factor 2, right? So base is 18, factor 1 is 1, factor 2 is 18, right? That's what we get it. And if that factor is 1, right? So you know that if factor is 1, you don't have to do much. So if it is just 1, that's the first time you are computing it. So just set the base is 2 and the so in the power map you set it as 1, so 2 to the power 18, right? Because f1 will be 1, f2 will be 18, so base will be 2. So in the power map, set 2 and 18 to be 1. That's what you have to do for this base case, right? Now let's consider a case like 2 power 9, right, where you express 2 power 18 as 2 power 2 power 9, right? So now you come to this part. So here what we will get. So here, here we, in the second iteration of this factory, so 1 comma 18 would have been finished, and second it would have got 2 comma 9. So 2 comma 9 would be split, and f1 will be 2, f2 will be 9. So now you swap like base is 2 and 2 and 9 will be factors. So now you come here. So it will come. So now you check, right? So if f1, if the factor 1, right? So is 2 less than or equal to the minimum power threshold of the base. So now you remember that helper method, right? So if 2 power 2, what we are asking is, instead of evaluating 2 power 2 and then telling 4 is less than 100, I am asking if 2, which is, so shall I evaluate 2 to the power 2 is what I am asking, to avoid one unnecessary computation. So the 2's least power, which is less than 100, is 6. So now obviously 2 is less than 6. So this will return 2, right? Because the first factor 2 is less than the minimum power threshold, which is 6 of the base 2. Now what we do, we compute the new base. So now we say like, okay, find the base of 2 to the power f1, which is 2. So now the new base will be 2 to the power 2, which will be 4. Now we say power map of 4 and 9, right, which is what we got. So 4 power 9 is what we are setting it to -1. Then you swap it using the ulta power, right? 9 and 2. So 2 and 9 we finished. Now let's do 9 and 2. Now again you ask this whether f2, right? So now if you see f2, so 9, so is 9 less than the minimum threshold of the base? Because 2 power 6 itself is 64. So 2 power 9 is obviously greater than 100. So 9 is greater than 6. So obviously this will not go into this, and this will not be set. There is no need to set 512 power 2. So if we don't do this, we will get an index out of bounds exception, right? So that's the main reason we do this. So we don't have to set up 512 power 2 as we have written it here. Now you do it for 3 comma 6 in the next loop. We'll just set this up, right? So in the next loop, when you set it up, then 2 power 3 also will be 2 power 3 power 6 also will be set in this if condition, and 2 power 6 power 3 will be set in this if condition. So that's how this swap factors will be called for every factor power, right? So for every factor pair, right? So for every factor pair of that power, right? So if the power is 18, so for every factor pair of that power, the swap factors will be called, and the bigger powers which will give -1 will be set here. And now here we have the corner case. If the base is a perfect power, right? So if the base is so perfect power is a helper method which we have wrote. So all that we say is like if a number is a perfect power. So this anyway, I will check in the code in my GitHub. You could figure this out. But all that you are trying to see is if a number is multiplied by a certain number of times to find if it is a perfect power or not, right? Like 8 is found by multiplying 2 into 2 into 2, or 64 is found by multiplying 2 6 times, or 4 I don't know, 3 times, right? 4 into 4 into 4, right? So that's this logic, right? So this is a perfect power logic. This is a helper method. So give an input number, return whether it's a, I mean, it's not a return, it will return the string of its perfect powers, right? So because a number can be expressed as a perfect power of two ways, right? So take for example 16. So 16 can be expressed as 2 power 4 as well as 4 power 2, right? So that's why we return all the perfect power combinations. And so once we know that if the base is a perfect power, so then we check and get all the perfect powers, right? So we just call this method to check and get all the perfect powers, right? So that it returns in that same way. So I'm following the same notation of appending it, right? So what are all the perfect powers of that? So once you do that, then you just have to loop through that. So you have to like do the same technique here. So go one more level down, like how in the Inception movie, right? So go one more level deep down and express the base as the perfect power and swap the power, right? So that's what we do here. So for each factor pair, for we are in the loop of factor pair. So within the loop of a particular factor pair, right? Like 2, 9 or 3, 6, within one factor pair, after swapping the factors with the direct base, then we find if the base is a perfect power, and we find all the possible ways of those perfect powers and loop through that and then get the power base, and then we find out what is the new base and what is the new power, right? So the new base will be like by swapping, right? Like 2 to the power, like that's what we swap. So p base and p power, this just that new powers loop we are doing. So if you just do that, you will get the new base, which is like 2 to the power 4, and the new power will be 3 into 17. That's what we do here, right? So 3 into so new power into the second factor, and the base rise to the power first factor, right? So that will be like, you call that and again swap it on perfect powers with the new base and the power. And all that you have to do is, if the new base and new power is less than 100, and if it is not set, then set it to -1. So that's all we have to do here. And I think I know I have rushed through the last bits of code, but once you check out this code and put some loggers and run it for yourself, you'll exactly know the nitty-gritties. It is just a programming implementation of this idea that we just talked about here, and you just run this. You will get how many distinct powers are present. So 9,183 distinct terms are present, right? So you could verify that. So total number of distinct terms should be 99 cross 99, right? So 99 cross 99 is something 9801. So it should be less than 9801, which is 9183. And I'm doing the same computation using direct method and comparing it is the same. And just submit the answer, you will be right. So this is a way we can solve the distinct powers problem in Project Euler. Thank you.